Hey everyone. So in the next couple of sessions, we're going to be talking about the Big Bang Theory, the timeline for the Big Bang, and the evidence that we have in support of the Big Bang. But before we get into that, there are some technical notes that we're going to be going through. So I wanted to spend a little bit of time just going through some of the background information before we jump into the Big Bang, because we're going to have to be talking about some ideas in particle physics, the structures of atoms, the fundamental forces. So I wanted to spend this time just kind of going over some of that key information. So a couple of important points to review. First, we talked about Hubble's law, where Edwin Hubble was able to identify that all distant galaxies are redshifted, and the greater the distance, the greater the redshift. Basically, if we are at larger distances, that object is going to appear to be moving away from us at faster and faster rates. And this was a first initial sign that space itself, the universe itself, might be expanding. There's two important points about this expansion. So again, Hubble's law implies space is expanding. And then we talked about how, we'll talk about this in a little bit, but we talked about how general relativity, Einstein's understanding of gravity, actually gives a very natural framework in which the geometry of space-time can be the thing that's actually expanding on very, very large scales. But before we get into that, we want to talk about two important points about this expansion that are known as the cosmological principle. And these 2 points are that on very, very large scales, the universe is homogeneous, so no special locations, and isotropic, no special directions. So on very large scales, space is, homogeneous, so no special direction. So let me actually back that up just a little bit. On very large scales, there's no special locations. And no special directions. When we look at the expansion of the universe, the manner in which it's expanding, the pattern that we see where more distant objects are moving away from us more rapidly, we said that all observers, no matter where they are in the universe, will see this same effect, that all objects are moving away from them, and the further away that object is, the faster it's moving away. So there's no special locations, and again, also on very large scales, no special directions. The way that space is expanding this way looks exactly the same that space is expanding this way. We'll be talking about this in more detail later, and in a couple of sessions when we talk about the cosmic microwave background radiation, the leftover light from the Big Bang itself, we're going to see this cosmological principle come into play even more specifically. Again, this cosmological principle is only on very, very large scales, looking at sizes larger than galaxy clusters. So on small scales, we can see, oh, there's some regions where there's lots of galaxies, other regions where there might not be very many galaxies. But if I look at a section, say like this, then a section like that over here looks pretty much the same as a section like that over here, looks pretty much the same as a section like that over here. On very, very large scales, we have this cosmological principle coming into effect. We talked about how general relativity comes into play and saying, well, our basic understanding of gravity, according to Einstein, is that matter and energy change the geometry of space and time, and the geometry of space and time tell matter how to move. And the expansion that we see from Hubble's law matches the cosmological principle. There seems to be no center to this expansion, There's no edge of this expansion. The expanding universe isn't expanding into some other empty region, because there would be some special locations. There would be a center to that. You could be on the edge where, oh, this is the direction where empty space is, and this is towards the center of the universe. But that both of those ideas violate the cosmological principle. So we have this idea that if space itself is expanding, then when we look at more and more distant objects whose light had to have been emitted from further and further into the past, the further the object is, the longer ago it emitted its light, so the more the universe has actually expanded since that time. And as the universe expands, the wavelengths of those light expand as well. That's where we get this cosmological redshift from. Again, if the universe is expanding, then in the past, the universe must have been smaller. And it's, again, the geometry of space itself is expanding. So when we talk about the expansion of space, the geometry of space itself on large scales is expanding. I'm actually going to write that down here. So on very large scales, is expanding. And again, with space itself expanding, it's not an explosion of some material into some larger empty space, because again, that would violate the cosmological principle. There would be some locations inside of that explosion, some locations outside of that explosion. That would be special locations. So you could not be at the center of this expansion. You could not be at the edge of this. So there's no, for this expansion of space, there's no center or edge. Because both of those would be violating the cosmological principle. No special locations or directions on these very, very large scales. So that kind of summarizes what we've talked about with Hubble's law and the expansion of space and introducing this important cosmological principle. We're also going to have to talk a little bit about particle physics. Let's talk about that. We've talked about how atoms are made of protons, neutrons, and electrons. But we can get yet smaller particles called quarks. So let me see if I can kind of list out the hierarchy of what things are made of. So we have our, what would be the easiest way to do this? Let's say we've got elementary particles. As far as we know, when we talk about elementary particles, we're talking about things that are not made up of anything smaller as far as we know. So the elementary particles that we can talk about are quarks. These quarks can actually come together to form protons and neutrons. So, and as far as we know, the quarks are not made up of anything smaller. Electrons are also elementary particles. As far as we know, electrons are not made up of anything smaller, as are photons. So, quarks, electrons, and photons are all elementary particles. As far as we know, they're not made up of anything smaller. There are a couple other elementary particles. Neutrinos, for example, are elementary particles, but we're not going to worry about that right now. So if I take a bunch of quarks and combine them together, I can make protons and neutrons. I can combine protons and neutrons together to make atomic nuclei. If I combine a bunch of quarks, I can make a proton or a neutron. If I combine a bunch of protons and neutrons, I can make atomic nuclei. And if I combine electrons and atomic nuclei, I can make neutral atoms. Now, typically, as I raise the energy, I will take these objects and break them into their constituent parts. If I start with some atoms and start raising the energy, I will break that atom into an atomic nuclei and rip the electrons away. If I continue to raise the energy, so these objects break apart at higher energies. So again, if I have an atom, an atomic nucleus with a bunch of electrons going around it, as I increase the energy, those electrons eventually get ripped away from the atom, and I'm left with free electrons and atomic nuclei. If I keep on raising the temperature, I'm going to have the atomic nuclei, the protons and neutrons that are in there, eventually get hit by photons that have so much energy that it rips them into their constituent protons and neutrons. If I go up to even higher energies, I've used that energy to break atomic nuclei into protons and neutrons. I can even break those protons and neutrons into their constituent quarks. So as the average particle's energies increase, we break these things into their constituent parts. This is going to be really important in the early stages of the Big Bang, where the universe was in an incredibly hot, dense state, where the particle energies were so high that we're going to just start with these quarks, electrons, and photons, these elementary particles. We also are going to want to talk a little bit about antimatter. So antimatter, it is like ordinary matter, but has the opposite charge. But the opposite charge. And there's two primary reactions that we're going to go through with matter and antimatter. We have what are called particle creation reactions, where I can have two gamma rays. Let me draw this one out. I can have two gamma rays, which again are the highest energy light per photon. These have to be very, very high energy photons in order to do this. They can actually come together and produce a particle and an antiparticle. We call this a particle creation reaction. The other reaction is the annihilation reaction. If I have a particle and an antiparticle come in, that can actually, they will annihilate with each other and produce two gamma rays. So this is the annihilation reaction. And both of these reactions involve the conversion of energy to mass and vice versa. In the first one, we start with these high energy photons. They have lots of energy. and that creates some mass, the mass of the particle and that antiparticle. In the other reaction, when we have this annihilation reaction, we have a particle and its antiparticle. Their mass comes together, and that's converted into pure energy in the form of 2 gamma ray photons. So this E equals mc squared equation is going to come into play for both the particle creation and the particle annihilation reactions. And this is something that's going to be going on in the very early universe. So again, basically we can convert between energy and mass, this matter and antimatter pairs. I think this is one of the last things for talking about this particle physics stuff. Talking about the fundamental forces. There are 4 known fundamental forces that are forces that are not the result of any more kind of basic forces. We've got the strong force. This binds quarks together in this is the force that actually allows the quarks to come together to form protons and neutrons and holds atomic nuclei together. So binds quarks into protons and neutrons. And holds together atomic nuclei. That's the strong force. We've also got the electromagnetic force. This is if I have a 2 positive charges, they will repel, and 2 opposite charges will attract. We have the weak nuclear force. We actually talked about this weak nuclear force briefly when we talked about the nuclear reactions that are going on inside of the sun. It's anything involving neutrinos is generally going to involve the weak force. It's responsible for certain types of radioactive decay. That's basically all we're going to say for this weak force. So weak force, that's involved in radioactive decay. In neutrinos and radioactive decay. And last, and in terms of strength at least, we have gravity. Basically, masses attract each other. And these 4 forces, as far as we know, these are the only 4 forces of nature that are fundamental. We have lots of other kinds of forces, like if I push on something, there's a force there, but that pushing force is not fundamental because it's the result of electrons in the 2 surfaces of my hand repelling each other. When those electrons get very close together, that's what's causing this particular pushing force. Okay? There may be other forces, but these are the only known fundamental forces. And this list is listed from weakest force to strongest force. So gravity is, in fact, by quite a wide margin, comparatively the weakest of all of these forces, which kind of seems weird because sometimes we talk about gravity being very, very strong. The one advantage that gravity has is that it is always an attractive force. So if I have a lot of mass in a really, really small location, only then is the gravitational force going to be very significant. as a comparison, let's think about my calculator here. Let's think about the forces that are acting on this calculator here. Right now, the gravitational pull from the entire Earth is trying to pull this thing downwards. But I'm pretty easily able to counteract that force, even though it is the entire Earth's influence trying to pull down on this object. That's kind of an example of why we say that gravity is not a very strong force. So again, this is ranked from weakest to strongest. To strongest. Okay. So those are basically the ideas that we are going to be kind of hitting at one point or another when we start talking about this Big Bang model and the timeline and the evidence for it. We've talked about Hubble's laws for getting our first kind of look at the expansion of space. In terms of particle physics, we have these different kinds of elementary particles and how they combine together to form different materials. And that at higher energies, like we're going to see in the very early universe, these things tend to break down into their constituent parts. We're going to talk about matter and antimatter reactions, so particle creation reactions and annihilation reactions, all relating to each other using this E equals mc squared equation. And we've got these different fundamental forces. We're going to want to know what these fundamental forces are doing at different points in the Big Bang timeline. So before I end off this session and we have the next one going into more detail, I want to give a super brief overview of the general patterns that are happening in the Big Bang model. So the Big Bang model. Basically, the entire picture of the history of our universe is of expansion and cooling. Space expands and cools down. So overall, the universe is starting in this hot, dense state, as the theme song to the TV show Big Bang Theory states quite eloquently. The universe is starting in this hot, dense state, and from that state, the universe is going to expand and cool. So as a part of this, we start in a hot, dense state. And from that hot, dense state, it's going to expand and cool. As it does this, a few key things are going to happen. First, the forces, the fundamental forces, separate out. So we're going to get the appearance of all of those forces at a very, very early time in the universe. And then as the temperatures go down, matter is going to clump together. So as temp goes down, matter clumps together. And that matter clumping together, it's going to pretty much follow this pattern of particle physics. As matter clumps together, the quarks are going to start to come together to form protons and neutrons. Then there's going to be a time when the protons and neutrons are starting to form the first atomic nuclei. Then a certain amount of time after that, atomic nuclei are finally going to be able to capture electrons and start forming atoms. And then as time continues to go on, gravity is going to take those atoms and start pulling them together, making these protogalactic clouds, starting to form galaxies, the first generations of stars. And then all of those stars and galaxies are going to go through that star-gas star cycle that we talked about before, and eventually result in the kind of universe that we see around us. So matter clumps together, atoms start being pulled together by gravity to form early generations of stars, starting to fuse and make heavier elements. And that's generally going to be our quick overview picture of the Big Bang. So again, the universe is going to be expanding from the Big Bang. As the universe expands, it is going to cool down. So the temperatures are going from ridiculously high temperatures, like temperatures that it sounds like I'm just making things up, like a trillion Kelvin. I've had students before say, it sounds like I'm a little kid who just wants the biggest number ever. But those are actually some of the temperatures involved in the earliest moments of the universe. The universe is going to cool as it expands. The forces are going to separate out. And then matter is going to start clumping together from those subatomic particles to protons to atomic nuclei to atoms to stars and galaxies. So that's going to be this overall picture. And in some of the next sessions, we're going to look at different eras in this Big Bang timeline and kind of try to map out what's happening in each of these different eras. Again, going from this whole idea of expanding and cooling, starting out where the forces are separating, then matter starts clumping together. Then once we have stable atoms, eventually gravity is going to take those materials, any of those overdense regions, and start forming the first galaxies and the first generations of stars out of that, and they form and evolve through that star-gas star cycle. So we're going to be talking about the timeline for this. And once we've gone through the timeline, then we're going to start talking about, well, what is our evidence for why do we think that this actually happened? So those are all the topics that we're going to be covering in some of the next sessions.